Hey guys, what's up? We're back with day 70 here. Today we're looking at finally be able to solve some definite integrals. So in terms of solving definite integrals, we're going to look at what's considered one part of the fundamental theorem of calculus. So here's what it is. Right now we can solve these things for real. We don't have to do Riemann sums to estimate. Again, on the test, an AP test, you still absolutely have to do Riemann sums, which is usually in table form, because we don't have a function that we can do this to. But now we can get the actual answers. So let's take a look. Okay, so as you can tell by the title here, Fundamental Theorem of Calculus, this is a pretty important theorem. One might say it's fundamental, and one would be right. Again, there are two parts of the Fundamental Theorem of Calculus. This is considered by a lot of people to be part two, but we're going to talk about it first, and we'll talk about part one of the Fundamental Theorem of Calculus later. Okay, so here's what it says. Okay, so the first thing that we have to be careful with here is we're using f twice. So for derivatives, we talk about f and f prime. For antiderivatives, we talk about capital F and lowercase f. So the fundamental theorem of calculus starts out with, it says, let capital F, so this new function that's capital F, be any antiderivative of f of x. Okay, so instead of using f and f prime, or using f prime going back to f, they oftentimes in calculus let capital F be an antiderivative of lowercase f. Okay, but again, capital F could be lowercase f, and lowercase f could be f prime. But when you see a capital F for a function, they're usually referring to that as an antiderivative of lowercase f. So it's just good to be careful when you write things down, to be careful to distinguish between capital F and lowercase f. So here's what we do. If we want to integrate lowercase f of x, right, from a to b, here's what we get. If I do a definite integral from a to b of f of x dx, this is going to equal the antiderivative evaluated at b minus that same antiderivative evaluated at a. This is a really, really powerful equation here. We're going to be using this right now to evaluate definite integrals, but later on we'll use it to find either capital F of b or capital F of a, which again, it's just a very powerful tool for us to use. I want to talk about another interesting word in here, is this word any. We know from solving indefinite integrals, right, that there are infinitely many antiderivatives for a function, right? And we account for that by doing plus c, right? So if I did the integral of, just as a reminder, right, when I'm evaluating an indefinite integral like this, right, this is a power rule, so I would bump and divide. I bump the power up to the third, and then I divide my coefficient of 3 by 3, and I get 1, right? But I have you guys writing this as x cubed plus c. So there are, again, infinitely many functions whose derivative gives us 3x squared. right? X cubed works, x cubed plus 1 works, x cubed plus 20 works, x cubed minus 5 works. But for this, I can use any antiderivative that I want. Any one. So we want to make this as easy as possible on ourselves. So I'm going to kind of walk you through how we set these up and the kind of notation I want you to use. So let's change this indefinite integral into a definite integral. So let's do the integral from, I don't know, 1 to 3 of 3x squared dx. By the way, generally we put whatever isn't dx in parentheses. Sometimes I'll remember to do that, sometimes I forget. It's not a big deal. Okay, so now again, I have to come up with any antiderivative to 3x squared. Well, I know that my general antiderivative I write as x cubed plus c. But I can use any of them. So I could let c be any number. What you are going to really want to do is let c be 0. That's the easiest one to do. Okay, but I'll show you it doesn't matter what you let c be. It's going to work for any antiderivative. So we want to choose the easiest one. So when we do this, first thing we want to get what we're doing the integral of to be in a nice form, so that's easy to do an antiderivative, like ax to the n form, which it already is in. So here's what we do. Once you are ready to execute the antiderivative, I'm not going to write the big S anymore. I'm going to put what I have in brackets. So here's what it's going to look like. Okay, so I write this in brackets to indicate that I have performed the antiderivative. I no longer write the big S. And I'm going to write my limits right here of 1 and 3. Okay. Now again, so there's my antiderivative, x cubed. I could choose any one, so I'm going to let c be 0 here. And I'm just going to choose x cubed as my antiderivative. Now again, there's my antiderivative, right? So f of x was like 3x squared. Capital F is now like x cubed. So what I have to do now is I have to do capital F of 3 minus capital F of 1. Okay? Well, to do that, I'm going to, capital F of 3 would be 3 cubed minus 1 cubed. And when I solve that, 3 cubed is 27. 1 cubed is 1. 27 minus 1 is 26. So I get the area under the curve of the function 3x squared between 1 and 3 should give me an exact area of 26. Let's take a look at that on our calculator here to kind of see that this is true. Okay. I'm just going to get myself in radians. Doesn't matter for this problem, but for future ones it will. Okay. Now again, I want to show you on your calculator how you can perform an antiderivative. Or sorry, a definite integral. So here's what we're going to do. One way to do an integral is just through the main screen. We hit math. We can see here number 9 is function integrate. That's how we perform a definite integral. So when you hit 9, you're going to see this pop up, right? And now I can just test this thing out by doing the integral from 1 to 3. My function was 3x squared dx. And we see that we get an answer of 26, which is what we were able to get solving it by hand. Now again, on the AP Calc test, sometimes you'll have to do integrals using your calculator. That's going to be really easy, right, if you know the buttons and know how to get there. But oftentimes we have to do it by hand as well. Let's take a look at what this looks like through a graph. Again, my function was 3x squared. And I know, let's see, how big is this thing going to get? At 3, 9, 27. Let me just set my window so we can see this. So from negative 10 to 10. I'm just going to make my y max go up to 30. So again, here's what our graph looks like. And again, I found the area between 1 and 3 and the function. So that thing there kind of looks like a trapezoid. That area should be exactly 26. To do an integral through the graph, we hit second calc, and number 7 down here is our integral. Our lower limit was 1. Our upper limit was 3. Right, and we can see it fills it in, and it tells us that that is exactly equal to 26. Right, so the area right here of this shaded region is 26. Okay. Let me show you another one. Let's try the integral from 0. Let's try the integral from 0 to 4 of 6x squared dx. Oh, by the way, here's the interesting thing. Before you do that one, I just want to show you that it really can be any antiderivative. Let's say instead of using x cubed, I wanted to use x cubed plus 1 as my antiderivative. Now, I don't know why I would make it harder on myself, but it's just showing that this will work, right? Then to evaluate this thing, right, I'd have 3 cubed plus 1. That would be my capital F of b minus minus 1 cubed plus 1. If I evaluate this thing out, right, I get 27, 28 minus 1 plus 1 is 2. I'd still get 26 as an answer, right? So I can really use any antiderivative I want, but please let C be 0 to just make this easy. Okay, let's try this one. In fact, why don't you pause the video right here and solve this definite integral and see if you can get the right answer. So go ahead and pause the video quick. Try this one on your own. Okay, we're back. Here's what this should look like. Again, I want to find an antiderivative of 6x squared. Then I'm going to evaluate that at 4 and minus that antiderivative evaluated at 0. Again, I'm ready to do my antiderivative, so I'm going to put my answer in brackets. This thing is already ready to integrate, right? Because it's an ax to the n form, so I'm just going to bump and divide. I'm going to bump my x up to the power of 3, and then I'm going to divide 6 by 3. 6 divided by 3 is 2. So we should get an antiderivative of 2x cubed. Again, since it can be any antiderivative, let's make it easy and just use 2x cubed. I'm gonna evaluate this thing from 0 to 4. So here's what I'm going to get. I'm going to get 2 times 4 cubed minus 2 times 0 cubed. 4 cubed is 64. 64 times 2 is 128. Minus 0 cubed is 0. 0 times 2 is 0. And I should get 128. Again, we can double check this on our calculator. And again, I'll do math 9, integral 0 to 4 of 6x squared dx. Right, and I can confirm my answer of 128. Okay, let's go back and try another one. Let's try the integral from 0 to pi of sine x dx. So again, I need to come up with an antiderivative of sine. So what is the antiderivative of sine? Well, I know cosine's derivative is negative sine. So unfortunately, it's not just cosine, right? It's going to be opposite cosine. So here's what I'm going to do. I'm going to put my brackets. I'm going to throw opposite cosine x. And again, I don't have to worry about plus c because I'm just going to let c be 0 because the fundamental theorem of calculus says I can use any old value I want, any old antiderivative. Right? So I'm going to do opposite cosine x. I'm going to evaluate that from 0 to pi. So this tells me I'm going to have opposite cosine of pi minus opposite cosine of 0. Be careful here. When you get negative antiderivatives, you end up getting a lot of negative signs going on in here. So we just want you to be careful here. One thing that can help is just put the two things in parentheses. We're absolutely going to have to do that when we have bi or trinomials. All right, cosine of pi, right, on my unit circle, I know pi is over here. This point right here is the point -1, 0. Cosine is the x value. So cosine of pi is -1, but I want the opposite of that. So this ends up being +1, right? It's like -1, which is +1. Minus, okay, cosine of 0 is 1, but it's the opposite of that. So I end up with -1, which becomes 1 plus 1, which equals 2. And once again, let's take a look at that on our calculator to confirm. Math 9, integral 0 to pi sine x dx. Does give us an answer of 2. Let me try one more with the binomial, just so we're kind of used to it. Okay, so I'm gonna do the definite integral from 0 to 2 of x cubed plus 5 dx. All right, so once again, I want to come up with an antiderivative here. I'm going to do that antiderivative in brackets. So x cubed, I'm going to bump and divide. I'm going to bump this up to x to the 4th, and I'm going to divide 1 by 4, and I'm going to get 1/4. So I got 1/4 x to the 4th. Plus, well, it's a constant 5, right? When I do an antiderivative of a constant, I tack on x. So my antiderivative then is 1/4 x to the 4th plus 5x. And I'm going to evaluate this thing from 0 to 2. Now here's where we definitely want to use our parentheses. Anytime my antiderivative has 2 or more terms, you got to be very careful to make sure that you're actually doing capital F of B minus capital F of A. Right? So I want parenthesis 1/4 2 to the 4th plus 5 times 2 minus parenthesis 1/4 0 to the 4th plus 5 times 0. Okay, so now 2 to the 4th, I know 2 cubed is 8, so times another 2 is 16. So I get 1/4 16 plus 10 minus, this whole thing ends up being 0. 1/4 of 16 is 4. And I get 14 for my answer. Now as you're solving these, I challenge you to, after you get the answer, try to do it without a calculator. Right? and come back and actually try this thing. I got math 9, the integral from 0 to 2 of x cubed plus 5 dx. And I get 14 for my answer. Okay. So that is it for today's video. Have a great day. 2 chains. Bye.